It's your boy Joey OACHABRM Josh Abraham, or you could say Crakasub. And yes, I have an organic chemistry exam on this organic chemistry exam this Thursday, which is on 14th. 15th. That it's a Friday. It's an off. That's good. That's good. That's good. GPT new chat. I'm having an organic chemistry exam in 3 days. So I made this chat for me to clear my doubts. Chill, GPT, chill. We need one more big guy. The Deep Seeker. So how do I start? This is a question paper. This is the same question paper? Open the draw. No, it's different. Okay, this is the answer to those question paper, I guess. What else do I have other than lecture slides, web links? Web links to removing solvent by, let me see.
Welcome to this introduction course on rotary evaporation. Today we will show you how to correctly use a rotovapor in your lab. The rotary evaporator or rotovapor allows you to efficiently evaporate your solvent or separate solvents mixture under vacuum and low heating temperatures. Let's look at the individual components before we begin. Firstly, let's have a look at the heating part. This part consists of a heating bath and a heating medium, the latter being either water for moderate heating temperatures or oil for temperatures above 100 degrees. The flask with your sample, to which we will come to later, will be attached to the glass joint and submerged into the heating medium. Upon reaching the lowered boiling point, the vapor will then travel through the vapor duct into the condensation area. This area is cooled by a chiller or by means of tap water. It will then be collected as a distillate into the receiving flask.
We got exercise.
To reduce the pressure inside the system, one needs to have a vacuum source. Here we have a vacuum pump that allows evaporation at a reduced boiling point and pulls the vapor into the condensation area.
No need to play Apple.
We have an interface, which is the brain of the whole system. It enables the user to control all parameters from one single area and not setting them individually. And now, let's get to the sample. Here is our flask with the sample. We filled the 1 liter evaporating flask to half of its volume. The bigger the flask, the better, since the surface area will be bigger. Next, we attach the flask to the vapor duct and close the combi clip. We recommend not to tighten the combi clip too much, since we will be under vacuum. Now it is time to set the parameter into the receiving flask. To reduce the pressure inside the system, one needs to have a vacuum source. Here we have a vacuum pump that allows evaporation at a reduced boiling point and pulls the vapor into the condensation area. Lastly, we have an interface, which is the brain of the whole system. It enables the user to control all parameters from one single area and not setting them individually. And now, let's get to the sample. Here is our flask with the sample. We filled the 1 liter evaporating flask to half of its volume. The bigger the flask, the better, since the surface area will be bigger. Next, we attach the flask to the vapor duct and close the combi clip. We recommend not to tighten the combi clip too much, since we will be under vacuum. Now it is time to set the parameters. For the temperature, we recommend using the delta 20 rule. This means that the temperature between the heating bath and vapor temperature, as well as vapor and cooling temperature, is 20 degrees. In our case, we are using an ethanolic solution, so we will base our setting upon the thermodynamic properties of ethanol. We will set the heating temperature to 50 degrees and the cooling temperature to 10 degrees. Next comes the pressure. Since we target a vapor temperature of around 30 degrees, we look up at the pressure values for ethanol at that particular boiling point in the solvent table. As you can see, the desired pressure should be at 97 millibars. So now we go back on our interface and set the pressure at 97 millibars. Now it's time to start the distillation. Firstly, we start the chiller and check if the coolant is flowing by shortly squeezing the cooling tube. If you can feel a short pulse, it means that the coolant is running. Secondly, we start the heating and then we start the rotation slowly. Then we press start for the vacuum pump and we can submerge the flask deeply into the heating medium. Once this is done, we can increase the rotation speed to 280 RPM. This is the optimal rotation speed.
Oh.
The
Okay.
condenser loading is an indication of the distillation rate. You can check the condenser loading by looking at the droplets of solvents or by touching the condenser and assess where it is warmer. Right now, it's around here, so it's good. The maximum condensation level is at 75% and is shown by a line on the condenser. Here, it's great. If it goes above the line, then your pressure will need to be increased. If it's lower, then the pressure needs to be decreased. Now comes the end of the distillation. We need to choose between concentration or drying. In our case, we had to dry our sample, so as you can see, the sample is now completely dried and is a white powder. We know that the evaporation is finished because there are no condensation droplets falling from the condenser coils. Or we can also see that from a sudden decrease of vapor temperature. If, for your sample, you would need to concentrate, meaning that you need to have some solvent left in the flask, then you have to stop the process before complete dryness. In order to decide whether you should go for concentration or drying, you would need to know what is your next step. For example, if you need to do a purification with a liquid injection of your sample in the chromatography system, then you would need to perform a concentration. Now that our evaporation is over, we need to stop the system. We firstly stop the rotation speed and then the vacuum and aerate the system until it reaches atmospheric pressure. We then lift up the flask and stop the heating and the cooling. I can now detach my flask. Then we empty the receiving flask in order to make sure that our rotavapor will be ready for our next use.
So the one that is evaporated must be ethanol, I believe, right? That should be ethanol, but what's this white powder?
Our dry sample is now ready for further processing.
don't get it. I mean, it's still parsing. Okay. Completion deadline. What functional group gives the following signals to IR spectrum? Carbonyl group, typically for aldehydes, ketones, carboxylic acid esters, or amides. Nitro group or amide 2 band. 1700 is 1700 per centimeter and 2510 to 3000 per centimeters. Carboxylic acid. Question to distinguish compounds by IR. I need to know how do we get these numbers in IR spectrum? I see why. Not going to classes. Yeah, I'll be right back, people. I just need to just be right back. Maybe 5 minutes or so. Still have a new profile on Twitch. got back. Sorry for the delay, people. Where my tablet at? My tablet to start writing. So it's been some time since I used this. Maybe 1 or 2 weeks. And I'm glad it's back. Oh, oh, the pencil lane have charge. Okay. So my pencil is charging right now. Yep. Functional groups in IR spectra refers to the idea that different bonds in organic molecules absorb infrared light at specific frequency measured in wave numbers per centimeter. These absorptions tell functional groups as percent. Mm-hmm.
Imagine being able to build anything, for any reason, in any style, at any scale.
In this video, we're going to focus on IR spectroscopy, specifically how to use it to identify functional groups in organic molecules. So let's compare the carboxylic acid with an alcohol. When you have a carboxylic acid, you're going to have a very strong, very broad OH stretch. This OH stretch, it shows up at a signal between 2500 and 3300 centimeters to the minus 1, which is a type of wave number. Now, the carboxylic acid also has a very strong CO stretch. And the CO stretch, it shows up at a signal of 1700 wave numbers. Now, you may want to write these numbers down because you'll need it in order to identify these functional groups in IR spectrums.
Okay.
Now, the alcohol, it only has the OH group.
So it's 2500.
So it has a strong absorption around 3200 to 3600. So that's the OH stretch of the alcohol group. Now let's move on to our next two molecules, the aldehyde and the ketone functional groups. Both molecules contain the carbonyl functional group, and the CO stretch of these two functional groups is very similar to a carboxylic acid. It's around 1700. Now, the distinguishing feature between an aldehyde and a ketone is the CH stretch of the aldehyde.
What?
This signal here is the alkane CH stretch, which typically shows up for almost all organic molecules that has a CH functional group, and that's around 2900. So you'll see that for the ketone as well. But this part here, this identifies the aldehyde over the ketone. So the aldehyde will have a signal of around 2700 centimeters to the minus 1. So that is the aldehyde CH stretch. So that corresponds to that part of the aldehyde functional group. So that's how you can distinguish an aldehyde from a ketone, is the presence of this signal, the aldehyde CH stretch. Now let's compare the ester and the ether. The ester functional group has a carbonyl CO stretch of around 1700, very similar to aldehydes and ketones. The ether, it doesn't have the carbonyl CO stretch, but it does have a single bond CO stretch,
Oxygen. Oh.
and that is between 1000 and 1150. So something that you want to take into mind is that double bonds have higher wave numbers than single bonds. The C double bond O stretch absorbs at a higher energy than the CO stretch of an ether. And triple bonds have even higher wave numbers than double bonds. We'll talk more about that later in this video. For now, you want to take into account the type of carbon that is attached to the oxygen. That is, this is an sp3 carbon. Here, we have an sp2 carbon. So therefore, the CO stretch is going to be different. It's going to be higher. It's going to be between 1200 to 1300. And the reason for that is the resonance that can form here. So let's take this lone pair, let's form a pi bond, and let's break this pi bond. And now let's draw the resonance structure of the ester. And let's add the corresponding lone pairs. So we could see that the sp2 CO stretch of the ester has more double bond character than the sp3 CO stretch of the ether due to resonance. And why is that important? Well, as we've established, a double bond CO stretch has a higher wave number than a single bond CO stretch. So a CO stretch with more double bond character is going to have a higher wave number than the CO stretch with more single bond character.
This is your brain when you're struggling to focus. And this is your brain when you're in the zone, but getting in the zone.
Come on.
Now we do have an sp3 carbon attached to the ester. So therefore, we're going to have this signal as well for the ester on the left. We're going to have two CO stretch, an sp2 CO stretch and an sp3 CO stretch. But the ether, it only has the sp3 CO stretch. And so that's how you can distinguish between an ester and an ether. The first characteristic is the carbonyl functional group. That alone is enough to distinguish it. But the second thing is the presence of the sp2 CO stretch versus the sp3 CO stretch. Now let's talk about primary and secondary amines before we go into amides. Now the primary amine, which has two hydrogen atoms attached to the nitrogen atom, it will show up as a double peak with a signal somewhere between 3300 and 3500. Now the secondary amine only has one hydrogen atom attached to the nitrogen atom. And so it's going to have a single peak between 3300 and 3500. So that's how you could distinguish the
What?
amine nitrogen atom. Somewhere between. Now, the primary amine, which has two hydrogen atoms attached to the nitrogen atom, it will show up as a double peak. Signal, somewhere between 3300 and 3500. Now, the secondary amine only has one hydrogen atom attached to the nitrogen atom. And so it's going to have a single peak between 3300 and 3500. So that's how you could distinguish the amine, the primary amine, from a secondary amine. Now, the amide, it does have the carbonyl functional group.
So it's 3,000,
And so we're going to have a CO stretch very close to 1700.
yeah, whatever. Now,
And
whatever.
we also
yeah.
have the NH2 group, so we're going to get this signal as well, between 3300 and 3500. So to distinguish an amide from an amine, you need to look for the presence of the carbonyl functional group. And to distinguish a primary amine from a secondary amine, look for the double peak in the primary amine and a single peak in a secondary amine. Now let's talk about alkanes, alkenes, and alkynes. The alkane CH stretch, it has a signal of around 2900, which we talked about earlier. The alkene, C double bond C, that signal, it's a weak to medium signal, which shows up around 1660. Now, the C triple bond C of an alkyne functional group, that signal is also a weak signal, and it shows up around 2100 to 2200 wave numbers. Now, the next thing we need to talk about is the CH stretch of an alkene and an alkyne. So the double bond CH stretch of an alkene, it shows up around 3000 to 3100. So relative to the alkane CH stretch, it's going to be slightly to the left of it. So here is the alkene CH stretch close to 3100. Now, let's say if you have a terminal alkyne, and so you're going to have the alkyne CH stretch. This signal is even further to the left of around 3300. And so here is the alkane CH stretch, and then here would be the alkyne CH stretch. So this helps you to distinguish an internal alkyne from a terminal alkyne. And to distinguish an alkene from an alkyne, you could simply look at these two numbers. So let's talk about the effect of hybridization on a wave number. So here we have an sp3 CH stretch. This is an sp2 CH stretch. And here we have an sp CH stretch. So notice that as the S character increases, the wave number increases. The SP-CH stretch, it composes of 50% S, 50% P. This is 25% S, 75% P. So as the S character increases, the wave number of the CH stretch goes up. Now, going back to alkanes, there's two of the signals that you want to be familiar with. The first one is a CH3 bend, which has a signal of 1365 to 1385. And then the other one, it can vary between a CH bend, a CH
That is 1600. This should be 1600. And this would be this. What?
bend or a CH3 bend, and that can vary between 1400 and 1450.
What? If 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 this is we would this is this, then how is this this? I thought this would be this. What?
Now let's talk about the relationship between atomic mass and wave number. As the atomic mass goes up, the wave number goes down. So going from hydrogen all the way to bromine, we can see that the atomic mass is going up. But looking at the wave numbers, it decreases from 2900 centimeters to the minus 1 to an average of 550. And so there's an inverse relationship between atomic mass and the wave number at which a bond absorbs IR radiation. Now, the next relationship that we need to consider is the one between bond strength and wave number. As the strength of a bond increases, the wave number goes up. We know that triple bonds are stronger than double bonds, and double bonds are stronger than single bonds. Thus, triple bonds will have a higher wave number than single bonds. We can see that in the case of alkynes relative to alkanes, in the case of nitriles versus amines, and carbonyls versus a C single bond O stretch. And it makes sense because more energy is required to stretch a triple bond compared to a single bond, because it's harder to pull 3 bonds than 1. And since wave number and energy are directly related, triple bonds will show up at a higher wave number in the IR spectrum. So that's another thing you want to take into account when dealing with IR spectroscopy. As the bond strength goes up, the wave number goes up. Now, another topic that we need to consider is conjugation. So here we have a ketone that is not part of a conjugated system, and it's going to absorb IR energy slightly higher than 1700. So this will be around 1720. Now, for the conjugated ketone, it's going to absorb IR energy at a lower wave number. That is, in this case, around 1680. So make sure you understand that. Conjugated carbonyl groups, they will absorb IR energy at a lower wave number. Now, the same is true for the double bond of an alkene.
Wait
Here,
a
this
minute,
is
I just. Okay, I'm wasting time. I'm wasting time.
Unconjugated system. And now the same is true for the double bond of an alkene. Here, this is a non-conjugated system. And so this alkene will absorb around 1650, 1660 in that area. Here we have a conjugated alkene, and so the absorption is going to be less. This one is going to be around 1600. So conjugated alkenes, they absorb IR energy at a lower wave number than regular alkenes. So remember, conjugation can reduce the wave number for ketones and alkenes. Now, it helps to remember something if you understand a reason why. Remember, we said that double bonds absorb energy at a higher wave number than single bonds. Let's look at the conjugated ketone. If we draw the resonance structure, we can put a single bond on that ketone. Let me color code this. And now we'll have a positive charge here. So looking at the double bond of the conjugated ketone, and let's compare it to the double bond of the regular ketone. Which one has more double bond character? The answer is this one. This one has more double bond character because it can't become a single bond through resonance. The conjugated ketone, it can become a single bond through resonance, so it has more single bond character. And now let's think about this. We said that double bonds have a higher wave number than single bonds. So because this ketone has more double bond character, it makes sense why it would have a higher wave number than the ketone with less double bond character. So as we've considered before, as the bond strength goes up, the wave number goes up. Double bonds have a higher wave number than single bonds. So that's basically it for this video. I wanted to give you a basic introduction into IR spectroscopy. Now, I'm going to be posting another video that has a few practice problems where you can apply the information that you just learned. So,
Mach dir keine Sorgen, dein Brauns bestem Bodytrimmer.
What the
Für eine ultimativ sanfte und komfortable Rasur, selbst an sensiblen Stellen. Entdecke jetzt den Braun Body
What
Groomer
the?
7.
Something on the tip of my nose.
in this video, we're going to work on a few practice problems related to IR spectroscopy. Now, I did create another video on IR spectroscopy basic introduction. I recommend that you watch that first before trying these problems,
Yep.
if you haven't watched it already. So let's begin. Given this IR spectrum, which of the following molecules would best correspond to this graph? So one of the first things we could see is that we have a carbonyl CO stretch near 1700. Now, all of the molecules that we have in our answer choices contain the carbonyl functional group. So that really doesn't help us. Now, we do have a very strong, very broad OH stretch between, looks like 2700 to 3300. So this indicates an OH functional group, which means we could eliminate answer choice B and answer choice C, which don't have it. So when you have the carbonyl CO stretch and the OH stretch combined, that's it. So very strong molecules that we have are 1700. which of the following molecules would best correspond to this graph? So one of the first things we could see is that we have a carbonyl CO stretch near 1700. Now, all of the molecules that we have in our answer choices contain the carbonyl functional group. So that really doesn't help us. Now, we do have a very strong, very broad OH stretch between, looks like 2700 to 3300. So this indicates an OH functional group, which means we could eliminate answer choice B and answer choice C, which don't have it. So when you have the carbonyl CO stretch and the OH stretch combined, that's a good indication that you have a carboxylic acid. So right now, we're between choices A and D. The difference between choice A and D is the presence of the triple bond. Now, it's important to know that the C triple bond C stretch occurs at 2200. We don't have any signal at 2200. Therefore, we could eliminate answer choice D. So we could say that this particular graph corresponds to answer choice A. Now, let's work on our second problem. Which of the following molecules corresponds to the IR spectrum that we see on the screen? Is it A, B, C, or D? By the way, for each of these problems, feel free to pause the video and work on it. And once you have your answer, just play the video to see if it's correct.
With the
Spectrum that we see on the screen. Is it A, B, C, or D? By the way, for each of these problems, feel free to pause it.
2200. So this is, oh, there it is. Okay, so carbon oxygen bond exists. So this is OH. So this won't be here. Now these two are the these two will have the chance from these two. There is a cyclic double bond. There's a cyclic structure with the double bond. I'm going with C.
And work on it. And once you have your answer, just play the video to see if it's correct. So the first thing that we can easily identify is the presence of the carbonyl functional group.
Carbonyl, yeah.
That is the CO stretch at 1700. And for all of the answers, we either have an aldehyde or a ketone. Now, what else can we identify in this graph? Well, we do have our alkane CH stretch, which is present in every molecule. But note that we have a signal here around 2700. This is the aldehyde CH stretch. So we know we don't have an ester or a ketone or anything like that. We have an aldehyde. Thus, we can eliminate answer choice A, which is the ketone, and D, that's also a ketone. So only answer choice B and C have the aldehyde functional group. So we're between those two answer choices now. Now, what else can we see?
Okay.
Well, for one thing, we don't have a very broad OH signal. So that would eliminate answer choice C because that has an alcohol. We don't see that OH stretch.
Okay, I was wrong.
What we do see is a C double bond C stretch roughly around 1600. So this is it right here. And we do see the alkene double bond CH stretch around 3100. So this tells us that we have an alkene with a hydrogen on the double bond. So that would correspond to answer choice B. So answer choice B represents the molecule that best corresponds to this graph. Now let's move on to number 3. Identify the molecule that corresponds to this IR spectrum. So what do we see here? Looking at our answer choices, we have either an alkane, an alkene, or an alkyne. And we have two different types of alkynes. We have a terminal alkyne, where the triple bond is at the end of the molecule, and we have an internal alkyne. Well, we have our typical CH stretch at 2900, which can be found in any one of these four molecules. But note that we have a signal here around 2200, and this corresponds to the C triple bond C alkyne stretch. So we do have a triple bond in this problem. We have an alkyne. So we could eliminate answer choice B and C. The question is it a terminal alkyne or an internal alkyne?
I need to start writing this to know which are which. But I don't know, my mind is I'm a bit stressed out, not stressed out, I'm just a bit tired. I need to take a 15-minute nap. I'll be back in 15 minutes. I'm sorry, people. It's just hard for me to switch, and I need the pencil, this thing to charge. 15 minutes. I'll be back. Peace out, people. Hey, sir, set a timer for 15 minutes. the mic was off, so you guys did not hear anything. Well, I am disappointed in myself for not being able to respond to finishing. Well, I gotta go. I gotta clean the kitchen. Yeah, I gotta clean my room with the food stuff. What else? What else? Come on. I need to eat something. Sorry, laptop was never meant to be. Yep, I'll be right back. No, why is my notes open? To the YouTube. I'm back. But I need to go back, but I'm back right now.
To find that out, we do have another signal here, which is around 3300, and this corresponds to the alkyne CH stretch, which is only present for a terminal alkyne. The internal alkyne doesn't have a hydrogen attached to the triple bonded carbon atoms. So D is out. Therefore, answer choice A is correct. So that's how you could distinguish a terminal alkyne from an internal alkyne. It's the presence of the signal at 3300. Now let's move on to our fourth example problem. So looking at our answer choices, we have a ketone, an ester, an aldehyde, and an amide. Which of these functional groups correspond to the graph that we see on the screen? So let's identify the signals that we have. So we have an alkane CH stretch with a signal of around 2900. And we do have a carbonyl stretch, or carbonyl CO stretch, with a signal at 1700. Those are the two main signals that we have. So with this information, can we identify the right answer? Well, all of the answers have a carbonyl functional group. However, it helps to know what other signals should be present for the other functional groups. Looking at answer choice C, we have an aldehyde. we don't see the aldehyde CH stretch at 2700. So we could eliminate answer choice C. Now looking at D, we have an amide. We don't see the signal for the NH2, which should appear as a double peak around 33 to 3500. So we could eliminate answer choice D. Now looking at answer choice B, we have an ester. An ester would have a CO signal somewhere between 1000 and 1300. Since we don't have that signal, we know that we don't have an ester. So by elimination, the answer has to be a ketone, because this is all that will be present for a ketone: the alkane CH stretch and the carbonyl CO stretch at 1700. So A is the correct answer choice for this problem. Now let's move on to the next problem, number 5. So looking at our answer choices, we have an amine and we have a few benzene rings. So which of these answer choices will best correspond to the graph that we see? Is it A, B, C, or D? Well, the first thing we can notice is the signal at 33 to 3500. We have the double peak, so this corresponds to an NH2 group. So thus we could eliminate answer choice C because we don't have 2 hydrogen atoms on the nitrogen. Now how do we distinguish between A, B, and C? Well, we do have a C double bond C signal close to 1600. So this could be an alkene or a benzene ring. Answer choice B doesn't have that, so we could eliminate B. Now we do have a CN signal between 1000 and 1100, but that won't help us in this problem. There is one signal that can help us to get the answer. And you might be thinking it's this signal, but this is just the double bond CH stretch, which can be found in alkenes, but also in benzene rings. And for answer choice A and answer choice D, we have that. So how can we distinguish between A and D? Think about what we don't have, what's usually here. What we're missing is the alkane CH stretch at 2900. Answer choice A has the alkane CH stretch right here. Answer choice D, it doesn't have the alkane CH stretch. So because we don't have that signal at 2900, we can eliminate A, because A would have that signal at 2900, but D doesn't have the alkane CH stretch. So answer choice D is the right answer. Now let's consider number 6. So looking at our answer choices, we have an ester, an ether, and a ketone, and we also have a benzene ring. Which of these would correspond to the graph that we see? Well, the first thing that we can notice is we lack the presence of the carbonyl group at 1700. So right there, we could eliminate answer choice A and answer choice D. Now, looking at answer choice B and C, we have 2 ethers and a benzene ring. Automatically, we don't have the signal at 1600, which would give us the benzene ring, nor do we have the signal at 3100, which will give us the CH stretch of the hydrogen attached directly to the benzene ring. So we have none of those. Therefore, that tells us that we can eliminate answer choice C.
10 minutes.
Now for answer choice B, we do have the CO stretch. This is the SP3 CO stretch between 1000 and 1150. So that would correspond to answer choice B. Answer choice A, it has the SP3 CO stretch, but what we lack is the SP2 CO stretch. This SP2 CO stretch would show up at a signal between 1200 and 1300, but we don't have that. Nor do we have the carbonyl stretch at 1700. So we can completely eliminate answer choice A. So only answer choice B would make sense. So that's how you could easily identify an ether, using the presence of this CO stretch. So that's basically it for this video. Now you know how to use IR spectroscopy to quickly identify the functional groups that would correspond to a particular IR spectrum. Thanks for watching.
Gib deiner Dusche ein Upgrade.
Josh Johnson. Umbe Maire. ഞാനിപ്പോൾ എന്താ പറയുക. Shout out to Josh Johnson for checking out the stream. I really appreciate that, my brother. Appreciate that. So, functional groups in IR spectroscopy. What else? GPT? What are the range shown in IR spectroscopy for each how would it say, it's not elements, each functional groups or common $2,500, $3,200, $3,600. Alcohol, carboxylic acid, amines, alkanes, alkenes, alkynes, nitriles, carbonyls, alkenes, alcohols, esters, ethers, plus. So 1,700. Where is that? Yeah, that's carbonyls. Is that right? Yeah, carbonyls. 1,500. That's gonna be, oh shit. Nothing's up there. Nitro groups. Where is the nitro groups? NO is a symmetric stretch in nitro groups. NH bending in amines and or amides. Carbon-carbon stretching in aromatic rings. Amide to band in proteins or amides. Usually around 1,500 to 1,600. Nitro groups, okay. 1,700 to 2,700. That would be carbonyl again. No, carboxylic acid. $1,700. This is a classic carbon to oxygen stretch region found in the functional groups like ketones, aldehydes, esters, carboxylic acid, amides. The exact position can vary a bit. Ketones and aldehydes 1700 to 1725. So classic carbonyl stretch region. This range covers alcohol stretching of carboxylic acid. Distinguish compounds by IR, methanol and diethyl ether. Mhm. Can you see the question 3? The spectrum shows several key peaks through the exact value are visible in the image. Around the this would be 3,300 ish, and this would be 2,900 ish, 3,000, 1,500 ish, 800, 700. Oh, that's a lot. The following spectra is an accompanying compound. What are the peaks that you can identify in the spectrum? I don't know. I don't know, but I know that I don't know. I don't know. I don't know. Gotta go check if the food is ready. And think, what can I do? Different bonds vibrate at different frequencies depending on the types of atoms involved, the strength of the bond, molecular environment. The instrument measures how much R light passes through the transmittance or is absorbed by the sample at each frequency, producing an IR spectrum. A graph of absorbance versus wave number. Mhm. IR light source, a source that produces infrared radiation, often a heater, globular, or a Nernst glower. Sample holder for solids, KBR pellets, thin films, or ATR, attenuated total reflectance crystal. instrument measures how much air light passes through the transmittance or is absorbed by the deuterated triglycine sulfate, mercury cadmium telluride detectors. Computers converts the detector signals into spectrum and display absorbance by wave numbers. So what? Good question. The absorbance peak for a functional group is not always exactly the same for every compound. It can shift down depending on the chemical environment. Nearby atoms or groups can change bond strength, affecting vibration frequency. For example, carbon oxygen group next to an electron withdrawing group might absorb at a slightly higher wave number. Hmm. Functional groups like alcohol nitrile can form hydrogen bonds which broaden and shift peaks to lower frequencies conjugation. So the general range of each one is consistent and useful for identification, but exact peak position and intensity can vary somewhat depending on the specific molecule and conditions. It is accurate for identification, but is it accurate? Accurate? No. Depends on. Mhm. So this process is used mainly to identify unknown organic compounds. Exactly. IR spectroscopy is primarily used to identify unknown organic compounds by revealing which functional groups are present. Here's why it's so useful. Every functional group has characteristic IR absorption rate, like a fingerprint. By matching the peaks in the unknown sample's IR spectrum to know absorption rates, you can figure out which groups are in the molecule. This helps narrow down and confirm the structure of the compound. It often combined with other techniques like NMR, nuclear magnetic resonance spectroscopy for detailed structural info, mass spectroscopy for molecular weight and fragmentation patterns, UVV spectroscopy for conjugated system, but IRSQ can easy great for spotting key functional groups, especially carbonyls, hydroxyls, amines, amines, etc. Okay. Well, I gotta hit the kitchen. I gotta see how the rice is, how the chicken is. Be right back. What the what? We got the spoon. We got the. Okay. Got the oil. The phone. Keys out there. No, he's not out there. I'm back after cooking some food. Yes. So I will be ending the YouTube stream. I'm sorry for wasting your time, people. I need to get better. I need to be better. Yeah. I'll be ending the YouTube stream and restreaming again. Because, you know, I gotta look into this. But yeah. Peace out, YouTube.